Well, thanks guys for all coming out tonight on the weekend we all celebrate Her Majesty's birthday. I thought we'd give the give the three cheers and the national a break. Give it a miss. But anyway, thanks for that. So most of you know this is a 6 talks a series on galaxies this year. And out of all these 6 talks, I thought I'd bring together 2 main principles or take-home messages. There's only 2 take-home messages you get by the end of the year out of all these 6 talks. Is one, galaxies. What are galaxies? Consider galaxies gravitationally bound structures of gas, dust, and stars that are in turn embedded in huge, massive clouds of dark matter. That's one of the one things you take home. Briefly, you might say dark matter. Dark matter referring to the exotic particles that we haven't really got to grips with, don't understand or identify. You can't see them because they don't emit or absorb light, but you can see the effects from the gravitational effects they have on other objects around them. And the second point that you'll probably learn more out of talks 5 and 6 is that galaxies themselves, without big structures, the galaxies themselves really are just building blocks for much larger scale structures within the greater universe. So tonight's talk we're moving on to 3, structure of the Milky Way. So I know there's a few new people here, new members, guys. Any newbies? Yay! Oh, good to see you. That's great for coming out. You might think, oh gosh, what have I missed in parts 1 and 2? Don't worry, because Peter gave a couple of talks too. It's been a little while since we did 1 and 2, so I'm going to recap the main points in talks 1 and 2 tonight as well, for everyone's benefit, and for my benefit too, just to bring us up to speed. Then we'll move forward, talk about some new points in today's talk, namely we're going to talk a little bit more about the Milky Way structure and dimensions. We're going to introduce the concept of globular clusters and how they have been used as a tool to work out the dimensions of the Milky Way and where the Sun sits in that lot. We're going to talk about the velocities, the motions of stars around us, and how what information that is provided in our understanding of the Milky Way. In fact, it's the motion of stars, as you find out, that has been evidence for the dark matter, massive big halos around the Milky Way, and also they are evidence for the big supermassive black hole that resides at the centre of the Milky Way. And then we're going to talk really interesting thing on the spiral arms, the pressure density waves of the Milky Way that go to make up the beautiful spiral galaxy patterns. Then we have, and that's the advantage of coming to these talks. These talks, of course, are presented with YouTube, which you can view later on if you want to go over 1 or 2 points. But the advantage of coming to the talks here at the Star Dome, of course, is when I finish the talk for 30, 40 minutes or so, we're going to play a 30-minute recorded lecture from Alex Filippenko. He's a professor of astronomy in California, and he's going to go over all these principles, but with a little bit more depth and detail, and bring it all together, and you'll enjoy it more we've already discussed the topic. So it just brings it together quite nicely. We don't film that for obvious copyright. There's plenty of time for questions and general discussion afterwards. If you've got a pressing question during, don't be shy, just say yeah. So just let's recap what we talked about on talks 1 and 2. One of the first principles we talked about was variable stars. Stars spend most of their lifetime on what we call the main sequence. 90% of your life is on the main sequence, where they're happy and they're stable, they're fusing, nuclear fusion's going on at their core, and they're fusing hydrogen to form helium in their core. All's going well. All good things must come to an end, and eventually they run out of hydrogen in their core. So that stops, and you start getting hydrogen fusion in their outer shells. So it was once a stable star, yay big, starts to swell out. And as it swells, it starts to lose temperature, so it looks red. What I call it a red giant. That's fine, those red giant stars carry on for a short time. Slowly the pressure and the temperatures inside the core build up, and the helium, which was the product of the hydrogen fusion in the core, then ignites and it fires up and it goes through nuclear fusion, whereby helium fuses with other helium to form heavier elements and so on. And it's during that late evolutionary stage of stars that a lot of stars become what we call variable stars, whereby instead of being stable, they start to contract, they expand, they contract, and they expand. And as we see them, they get brighter, they get dimmer, and they get brighter, and they get dimmer. And there's all sorts of variable stars, but these sorts are called intrinsic variable stars. And there's two particular type of variable stars which are really of interest: Cepheids and RR Lyrae. These guys have been discovered that the ratio, the period, the time interval at which they expand and contract, expand and contract, is directly related to their brightness or their intrinsic luminosity or absolute magnitude. Now, so if you identify one of these stars, you see how often it contracts and expands, changes its brightness and so on. You can work out how bright it really is. You know how bright it appears through your lens of your telescope. So it's not too difficult to work out the distance between us and those stars. And that's the key. So these stars are very, very useful to work out the distances to them. You might think, oh, that's interesting, but so what? So the Cepheids are found in regions of star formation, and they are sort of a later evolutionary stage of young, large, bright stars, typically in regions of star formation. So you can see them from long distances. And it was actually Edwin Hubble who first identified some of these stars in what we now know as the Andromeda Galaxy. Up till then it was just called a bit of a nebula, a bit of a fuzzy patch in the sky, and that was the first evidence. Hey guys, there are other galaxies out here, we're not alone, we're there, you know, it's a bit wide world out there. So that's very relevant. We learned about Cepheid variables. RR Lyrae variables are the end result of much older, smaller, dimmer stars. And they predominantly reside in, which we're going to learn all about, globular clusters. And because they're a lot dimmer, you can't see them at huge, long distances like in other galaxies and so on. They tend to be more used as a tool for estimating distances to these globular clusters. The second point, or interesting thing that we talked about during our talks, was that same guy, Edwin Hubble, yes, of the Hubble Space Telescope fame. He started looking at all these galaxies when we suddenly noticed, oh, there's loads of galaxies out there and telescopes got better. So he realised there's all different types of galaxies, we better make some sense out of all of this. So he started classifying them according to how they looked optically, just through the plain telescope of visible wavelengths. And he really settled on, there was three main groups. 60% of them were what we call elliptical galaxies, about 30% were called spiral galaxies, and about 10% were just none of the above, irregular galaxies. So a little bit about them, elliptical galaxies. They tend to be spheroid in shape, almost like a football. They have a very large range in size, whereby you can get dwarf elliptical galaxies right through to giant elliptical galaxies. That's an important thing, a really large range in size. Interesting enough, there's no star formation, or very little star formation that goes on in those galaxies. Let's see what we've got going on here. Spiral galaxies, which of course the Milky Way is one of those, they tend to have that very narrow, small, nice, pretty shaped disk in them. their size range is quite narrow, and they're all roughly about the same size. So when you've seen one, you've seen all of them roughly in terms of sort of astronomical sizes. And it's those disks that are very active in star formation, a lot of star formation going in on them. The irregular galaxies, there's a small 10% of them. Usually there's something interesting going on there, like merging with other galaxies or some sort of interaction with other galaxies is going on, and that tends to be distorting their shape and throwing them out, and that's probably why they appear that way. Third thing we talked about the sort of general structure and dimensions of the Milky Way. Just summarising, we all know it's got that lovely disk. It's got a bulge right in the middle, and that's about 10,000 light years across, that bulge. A light year being the distance that light can travel in a year, which is about 10 million kilometres. And just that central bulge is about 10,000 light years across. You've probably heard of spiral galaxies when we talk about bar spiral, and it appears that our bulge has probably got elongated shape to it, which means it's a barred spiral galaxy. So like all good galaxies, there's always a bar at the centre. Nice. Then you've got the thin disk that goes out, and that's about across about 100,000 light years across. So if you look at the diameter, the middle is here to the outer part of the disk, the visible disk we're talking about with all the stars and the gas and the dust. We lie about 26,000 light years out from the centre, i.e. a little bit further than halfway out. Then you've got the spheroid halo, what they call the stellar halo, of less dense, it's more a less dense number of stars, but a lot of old stars, more dispersed out around there. And if we're talking 100,000 light years for the disk, that's about 130 to 150,000 light years, and that's surrounding the whole disk and bulge of sparsely, that's the word I was looking for, sparsely distributed old stars. So let's sprinkle it down to the apex. And then, as we talked about earlier on, that what we can see visible galaxy is then embedded in a large cloud, spherical halo of dark matter that's about 600,000 light years across, huge, to the point of the light and stars and gas and dust that you can see in the Milky Way, in most galaxies, is only about 10% of the mass of a galaxy. 90% of the mass of the Milky Way is this invisible stuff called dark matter that we only know is there by its gravitational influence on what we can see. And we're going to learn all about that later on. So that's sort of what the Milky Way looks like roughly. We then talked about star-making nebula. You look in these lovely books or on the internet, you see these lovely pictures and go, ooh, that looks nice, all those pinks and blues and stuff, that's nice. What am I actually looking at? Okay, so you start off with what we call a giant molecular cloud, a huge cloud of gas and dust that's cold and still, many light years across. Something will trigger it, will start rotating and collapsing in on itself. Stars start forming from that, and typically it's the big, large stars that form first. They fire up first. What do? They start blasting out high energy ultraviolet light. That ultraviolet light then ionizes, which means bump electrons off, all these little hydrogen. Remember, hydrogen is just a proton, electron. It ionizes, the ultraviolet light splits the electron off, and when it recombines back again, it emits a photon of light in red wavelengths. And that's called an emission nebula. Big giant stars blasting out ultraviolet light, ionizing the hydrogen, which then in turn glows. And that's what's causing this nice, pretty pink colour here you see in nebula. With the passage of time, your medium-sized stars then start to form, and they emit light, less energetic light, in the optical wavelengths, light that we love, shows us the way around on Earth and keeps our backs warm. And that light tends to get reflected off dust particles, which tend to be blue, the same reason our sky is blue. Light gets reflected off molecules. And that causes what we call reflection nebula. Of course, this region is very thick and dense in gas and dust in particular. You get little patches and little lanes of dust through here that causes the process of extinction, which means it absorbs and scatters light. You can't see through it. It sort of appears dark. And that's what they call dark nebula, these patches here. So that process is what's causing these emission nebula, the process of star formation from these large molecular clouds. With a little bit more time, slowly most of the stars get formed and they consume most of that gas and dust, and the remaining tends to be dispersed. And you end up with an open star cluster, and it's very relevant for later on. So you go through this process, large cloud, forming these lovely, beautiful, picturesque, very bright nebulae to form open star clusters. So that's our background, what we've covered so far, and is very relevant for today's talk. So we're going to talk a little bit about these subjects here, which we mentioned earlier on. So the Milky Way structure, we've got a bit of a fair idea now of the Milky Way structure and dimensions. There's just one little thing I wanted to add into it, and that's globular, these things out here. There's your bulge, there's your disk, there's your stellar halo. All that, remember, is embedded in that big giant cloud of dark matter. And you're scattered throughout the stellar halo. You've got all these big globules, and they're called globular clusters, and they're very important. So that was the only thing I really wanted to add to the Milky Way structure there. So let's talk about these clusters. First of all, star clusters. We talked about open clusters, and that's the Seven Sisters, or Pleiades, or Matariki, which is coming up on the horizon at the moment, which we all celebrate, the Mara New Year. The Japanese call it Sabaro for their New Year, hence the Sabaro cars and so on with the 7 stars on. And that's an open star cluster of new, young stars. Typically, there's a few hundred, sometimes up to 1,000 or so, loosely gravitationally bound together. They form from a big cloud, and eventually they will disperse in a few million years' time. Now, in contrast, you've got these other little clusters of stars which you can see, and they're called globular clusters. And they typically hang out in the halo of the Milky Way. There's about 150 or possibly up to 200. They haven't identified them all yet. These guys, instead of a few hundred to a few thousand stars, you're talking tens and hundreds of thousand stars, and some of them over 1 million stars. Typically, they're old stars, the oldest stars in the galaxy. 12 odd billion years old. This huge collection of stars is tightly gravitationally bound together, and that's why they've lasted so long without dispersion as opposed to your open clusters. So 2 totally different types of star clusters you get in the Milky Way. Hold that thought. So there's the 2 common ones that we see down here. No doubt most of you have probably seen it with your telescope. If you haven't, do try and get a look at them. They're gorgeous to look at. Omega Centauri and 47 Tucanae, and that's really what you see, like a big fuzzy blob of cotton wool, magnificent. And there is millions of stars in there, old stars, tightly gravitationally bound together, typically in the halo of the Milky Way. Now, and this brings us on, because we talked about Seyfert variables, which are from bright young stars, and they tend to hang out in star formation regions. Now we're contrasting the other type of variable stars that you can tell the distances to, and it's these RR Lyrae stars. These guys are old stars. What I've got here, old stars in the globular cluster. Yep, and you've made the right assumption with the link. These globular clusters have many RR Lyrae stars inside them. So that enables you to map out the distances and locations to these globular clusters. And that really is the key here. You're able to map your locations, and that gives you the key of where they are. It gives you an idea of the dimensions of the Milky Way, and indeed that's what the slide here to show you is. So suddenly all these globular clusters scattered around here, and suddenly now you're fully aware, hey, look at our Lyrae stars, the way they pulsate. We can from there deduce how far away each of these are, map them by their distance and their direction, and that gives you an idea of the size of the star halo. So that's one of the other principles that I want to come out of tonight, is to show you how through just learning about some simple principles from interesting little features in the Milky Way, you can then deduce and work out the real structure and size of the Milky Way. In case you're wondering, how do they know that stuff? This is how they do it. So, stellar velocities, how stars move, and you might think, oh, big deal, so they study stars, how they move. How they do it is actually shown nicely in the movie clip, and they go through a little bit of depth of that, but the importance of it, it's how the stars move is the evidence for the dark matter halo and a big central supermassive black hole. So let's look a little bit further into that. And what they do, they're able to determine the velocities of these stars and also the gas further out in the disk of the Milky Way, and the movie goes over how they do that with radio astronomy. They map it. Here's your distance out from the centre, and thousands of light years. Here's the velocity of the stars, and you'll see the velocity goes up as you'd expect it to. Now, they've got this dotted line as if there was just stars and gas and dust, you'd expect the velocity to go up to a certain point, and then just slowly start to drop off. But when they measure the velocities, look what happens. The velocity goes up, and it keeps going up, keeps going up, and keeps going up. And there's only one thing that will do that: mass, other mass. That's how they know there's dark matter out there. So it so happens they'll go with the movie that we're travelling about, in case you're wondering, about 200 kilometres per second around the centre of the Milky Way is what we're travelling at. And if you do your math, it works out to about 260 million years for us to do a loop around the galaxy. So the last time we were in this position of the galaxy, the dinosaurs were roaming around. Who'd have thought? The other thing they did with more technology, they were able to see through a lot of the dark dust in the Milky Way through infrared, high definition and high resolution infrared telescopes. And they were able to identify some stars, some key stars, orbiting around in the centre of the galaxy. And there was a handful of these stars, and they were able to map out the exact orbital properties, the velocities, the orbital paths, and so on. And it wasn't hard once you mapped these out to work out they're actually orbiting something bang smack in the middle. And by analysing the orbital properties, including the orbital velocity, you're able to actually calculate the mass of that object and its size as well. And they deduced it was something of about 4.3 million solar masses. A solar mass being the mass of our sun, which is about 2 times 10 to the 30 kilogram. In the movie they mentioned 3.6 million solar masses. Don't get put off by that, it's just that they've got, since the movie was done, they've got better at refining it, and the new calculations suggest about 4.3 million solar masses. And they also have yet to sort of sort out the exact size of it, but the object they're orbiting is probably in the order of about 17 light years across. You might think, that's a big distance. When you're talking light years, sorry, light hours rather, yeah, light hours, you might think, that's a decent size. That actually goes out about the size of the solar system. I think it's many hours, about twice that size, isn't it, the solar system? Yeah, it's about, I think light's about 5 hours to get out to Pluto and so on.
That's actually an upper limit, Chris.
Yeah, that's the upper limit, yes, correct, yeah. And there's a telescope called the Event Horizon telescope, which is just come online, which I hope to see the event horizon. But the bottom line is That's a relatively small size in astronomical terms. That's a huge mother of an object you've got sitting there. There's only one thing it could be, a supermassive black hole. So that is the evidence by studying the stellar velocity. So you can see, once again, just by making some simple observations, you can deduct from there the structure of the Milky Way and what's going on. And we move on. Okay, good. Spiral arms. It's an interesting thing that separates us from elliptical galaxies. It's intuitive, and you'd be forgiven for thinking that when you look at a picture of a spiral galaxy like this, you see these lovely big spiral arms brightly lit up. And you'd be forgiven for thinking that in that galaxy, in that disk, there is concentrations of stars in these spiral patterns. And that's what made up the disk, just spiral concentrations of stars. If that was so, knowing what we know about the rotational rates of galaxies, you'd expect, if you think about it, those spiral arms would slowly start spiraling within themselves and just end up a mess. But that doesn't happen. Something else is going on. And the evidence suggests that when you look at something like that, you've got a disk, a big plane of a disk, and that disk is evenly distributed with stars and gas and dust evenly throughout it, all going around the galaxy at, say, 200 kilometres per second. Superimposed on that and moving independently, you've got these areas of increased pressure and density, compression, and they are in a nice spiral pattern. They're moving superimposed on the disk independently at a slower pace than the 200 kilometres per second. They're moving at a slower pace and they're just moving through. So you've got the disk of stars and gas evenly distributed, zipping around, and then you've got these spiral-shaped areas of concentration pressure that are moving a lot slower just around the Milky Way. So from there you think, okay, so the stars are going quicker, they're going to catch up to this area. That's exactly what they do. So these big stars and clouds of gas and dust come zipping around. Oh, here we go, we're going into one of these regions of increased pressure. And what did we talk about? We talked those emission nebula and so on. When gas clouds and full of dust and gas go increased pressure, they start compressing down, condensing. What happens? You start getting big stars, you start getting emission nebula, nice and pink and red, you start getting the blue reflection nebula, you get more stars forming, and suddenly you've got this big, bright, colourful region, big, hot stars with a blue tinge to them, these lovely big colourful emission nebula. Yep, your secret variables are in there, let's throw them in there as well, blazing away. And they're in this concentrated area. Eventually they move through that area because they're going quicker, and they move out of that region. And that is why when you look at these sort of pictures, you see these lovely lit up spiral arms. The dark patches in between aren't void. They're full of just as many stars and gas and dust. It's just they're not blazing away and lit up like Christmas trees. They're there, but they're just, you're less able to see them. Next slide. This just illustrates that a bit more. The guy, actually, Alex, does a wonderful job explaining an analogy. And one way of looking at it is, and you see this happen on the motorway, something will be slowing the traffic down. It might be a slow-going tractor or something like that, and you can't. So the tractor's going slowly, you come zipping along at 100 k's an hour, you slow down, you go past it, and then you speed on again. And that's exactly what's happening. And how many times do you go down the motorway and you suddenly see all the cars are slowing down and they're getting close together, and you look around, where's the accident or whatever, and it clears again and away you carry on again. And that's actually a natural phenomenon, like a pressure density wave. And that, if you go back to that same spot, half an hour later, that area of the cars slowed down. It's actually a few kilometres on. That little, you see it on the motorway. And once you're aware of that now, you make that little observation to yourself. It's like a little mini pressure density wave just moving down the motorway. And if there's, you can't put an explanation behind it, it just seems to be a natural phenomenon. So here, in this, is you've got the star, or gas cloud rather, coming up here, it's zooming up the lines, it's going quicker, it's entering into this area of increased pressure, you're getting new stars and nebula forming, and they are going quicker, so eventually these star clusters that come out the other side start to move on again, and new gas and dust comes in here. So that's quite well explained in the movie as well. So that's really what we've covered, the Milky Way structure, globular clusters and how they're a useful tool using the variable stars to shape out the stellar halo, how it's the stellar velocities that is evidence for the dark matter halo that's further out, and also the supermassive black hole in the centre. And we all take for granted these spiral arms. I think that's it. I remember learning all about that, just fascinated by those spiral arms. So that's an interesting point, and that's an important point. So we're going to move on to the movie, and but briefly, any questions around any of that? Yeah.
Are these serious of increased pressure due to dark matter?
No, it doesn't appear to be. What causes them, that natural phenomenon, and it appears to be in the computer simulations, if you get galaxies interacting, and you might think two galaxies are far apart, but remember each galaxy, from what we see, is embedded in these huge big clouds of dark matter. And you get the whole galaxy, they're interacting a little bit, and it seems to be a natural phenomenon with computer models that eventually spiral densities seem to form, and it doesn't appear to be related to the dark matter. As for the distribution of the dark matter, it appears to reflect these proportionally seems to reflect the amount of boronic matter, stars, gas and dust we can see. And there's sort of, say your cloud is out there like that, your galaxy in the middle, and say the concentration of boronic matter goes up like that in the centre of the disk. The dark matter concentration does go up a little bit as well, but nowhere near as much. But proportionally it seems to go up. And the reason you might say, well, just a few minutes ago there was much more, 90% of the mass. It's that the boronic matter makes up yay big, and you're talking, 600,000 light years, so that's why the volume. But to answer your question, the reason behind the spiral structure seems to be more something to do with interactions, gravitational interactions. Things are rotating, when things rotate and they react, things happen, and that seems to be the case.
How do you measure distances to distant objects?
So,
how do you measure distances to distant objects?
Yeah.
By parallax or some other?
So you know how bright something is, and you know how bright it looks from here, and you're asking how do they calculate that distance? Yeah. They count by the inverse square law, that when light goes out from a source, on a certain distance, it gets quartered. Say if you go, say, factor of 2 distance out, it spreads here, 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 and here. So it's 1 over 2 squared, which is 4 times. If something goes out further again, it goes 1 over 4 squared, which is the 16th, the intensity. So it's the inverse square law of the intensity of light. And there's a formula, it's called the distance modulus formula, whereby you just plug in the distances or the magnitude, apparent magnitude, what it looks like from the Earth, with the absolute magnitude, it's intrinsic luminosity, and then you calculate, I think it's 5 log the ratio minus 5. There's a formula for it called the distance modulus, but it's all based on the inverse square law. Yeah. Can you imagine light, how it goes out, spreads out, and gets fainter and fainter? So it's mathematically done.
Yeah, it still has to be calibrated by parallax, Chris.
Yes.
Because until you've measured one star's distance, you've only got a relative scale using brightness, so you need to measure the parallax at least some Cepheid variables or RLI variables.
Yeah, and that's a whole talk called the distance ladder. And there's about 5 or 6 different ways to measure distances to things at different relative distances further out, and they overlap one another, and Bill's quite right, you actually compare it with something else through a different method. And the method they use was parallax for measuring distance between stars, close stars. So yeah, that's a whole talk, but that's in principle that answers your question. If you, it's the inverse square law. If you see something that's so you know it's X amount of brightness and looks bright, certain brightness from here, you can calculate it. But it's a little bit more involved. I gave you a simple answer, but it's a lot more involved. It's called the distance ladder. If you've got one method that sort of gives you an idea up to here, and another method that up to here, and another method here, where you got that overlap, you try and compare and calibrate. So does that all make sense? Yep. All good. All good. Okay. So Steve, shall we see what we can do?